All right, so welcome to the first in a few videos of Unit 4 and 5 on confidence intervals and hypothesis testing. So what I want to talk about here, first you should have the guided notes. Now, if you're having trouble getting to where those are, what you need to do is go to the Unit 4-5 Moodle page and you download a copy of them right here. Now, if you can go to campus and print them, that's better. So, also, you're going to need to make sure you have this. That's my table of critical values. That's a table of critical values. Now, so that's what you're going to need. I have this on a separate printout here on OneNote, so I'll be referring to that back and forth every so often. So what this is our notes on confidence intervals and hypothesis testing. Now, we're going to learn some of the basics here in this first video, and throughout the course we're going to see what the connection is to hypothesis testing. Throughout the rest of this unit. So, I always like old comics, like particularly Garfield. High temperature will be between 40 below and 200 above, and Garfield points out, hey, this guy is never wrong. Well, that may be true. Now, the thing is, how useful is such a prediction when you think about it? Is that really a useful prediction, so to speak? Not really, but we're going to deal with it. So what we have, we're going to learn how to do confidence intervals in this particular unit so we can estimate the value of a parameter. So we're going to construct a confidence interval as well as reporting probabilities that describe what would happen if we use this confidence interval many times. So we've gotten through a lot of material quite so far, and here is the real meat of statistics, estimation of parameters. Now, we want to define a point estimate. Now, since we're going to be dealing exclusively with means, means and proportions, point estimate is a single value used to approximate a population parameter. So what happens is we estimate the population parameter mu with a sample statistic x bar. The sample mean is the most unbiased point estimate that's out there. So for example, an economics researcher is collecting data about grocery store employees in a county, and what you see is this data show the hours of 40 employees from several grocery stores. So if we want to find a point estimate of the population mean mu, so in other words, we have to find the sample mean. So we would just go into the calculator and enter that into a list, and we would do that, and what we would get here is 29.6. That's going to be the point estimate for the number of hours, the mean number of hours worked. So that here is in fact our point estimate. So an interval estimate is an interval or range of values used to estimate a population parameter. So one thing here, how do we figure out the size of this particular interval? Now, that's always a good question. How do we figure out the size, the size of this margin of error? Well, one thing that you'll notice is, it is in fact 2.1. And, margin of error, that is the distance between the endpoints and the point estimate. So that's what we're going to get here. Now, how we calculate that remains to be seen. So, but one thing is the interval is always going to be symmetric. So it's going to be the same distance on both sides. 2.1, in this case it's hours, 2.1 hours on either side. So how confident do we want to be that the interval estimate actually contains the true population mean mu? Now, truth be told, we don't know. We're doing pure estimation here. We're speculating based on a sample. Well, that's what we do in the real world. If we had everything that we needed, if we actually had all the true data, we would not be needing to do statistics at all. We would just say, hey, this is all the parameters, and we have them all. We're done. End of story. So level of confidence C is the probability that the interval estimate contains C, which is your population parameter. So basically, level of confidence is anywhere from 0 to 100%. Now, there shouldn't be ever 100% confidence, but sometimes we'll have something like that. But, well, no, 100% confidence just won't fly. So we're going back to the normal distribution here. We're going to learn some other distributions, particularly the t-distribution, a little later on in this course. So if it's a level C confidence interval, this area is C, or C%. And we can figure out the critical values. Now, the nice thing is it's always going to be symmetric. So the critical value is just going to be one single, it's going to be a plus or minus of the same thing. So for instance, if we have a confidence level of 90%, what that means is we are 90% confident that the interval contains the population mean mu. We're 90% confident. Now, if we want 90%, what happens here is this area in here is 90%. So what we would have to do is, well, one thing we know is if there's 90% in the middle, there's 5% on either side. Now, if we inverse normed the percentile, this mark is the 5th percentile, and this particular mark is the 95th percentile. Now, if we were to go ahead and inverse norm both of these, which you can see me do right here on my calculator, and well, it turns out the model I have here at home is the new one, but we're just going to assume that. So if I have 0.05 and then 0.95, I get 1.645 for the critical value. So what we're going to do here is we're going to find the critical values for the confidence intervals. So for 80%, what that means is we have, and that's not the best looking normal curve, but what can you do? So we have 80% in the middle. Now, if 80% of that is occupied, that means we have 20% left. So that means there has to be 10% on each side. So what would happen is we would inverse norm 0.10, or we could inverse norm 0.9. Basically, we'd get the same thing just with a different sign. So if we did that, 0.10 and 0.9 or 0.90, we get 1.282. So that's what we're going to get for the critical value, 1.282. Now, here's another interesting thing. So if you go to this table, Now, confidence level, so far we've done two of them. We've done 90% and then 80%. Now, degrees of freedom are something that we haven't discussed yet, don't worry. However, if you scroll all the way down to large, basically this is what gives you the critical z values. So all you have to do is take a look. So for 90%, which is right here, if we look at that z value, we get 1.645. Well, take a look, and we see exactly the same thing. Now, if we did it for 80%, we would have 1.282. Hey, guess what? It's the same thing. Now, unfortunately, 92% is not in there. There's always going to be like one question on your MyLab stat that asks you to find the critical value for something that is not on the table. I purposely did that because, well, I think it's good to know. It's good to know how to do. So what you can do is 92% is in the middle. That means there's 8% split, or 4% each. So this is the 4th percentile, and this would be the 96th percentile. So we have 2 percentiles that we can figure out. Either way, if we inverse norm, 0.04, we get negative 1.751. Now, if we did 0.96, we get positive 1.751. So altogether, the critical value is just simply 1.751. All there is. That's all there'll be to it. Now, for the 95% confidence interval, remember, 95% in the middle, that's the same thing as finding the middle 95%. And why my pen is doing this right now. There we go. So that means there's 2.5% on either side. So if I inverse normed, 0.025 or 0.975, let's see what we get. We get negative 1.96, and if I did 0.975, we would get positive 1.96. So, the critical value is going to be 1.96. Now, if we go to the table that I've given you, one thing that you should be able to see here, 95% confidence, 1.96, just like before. So that's not too bad. Now, yeah, so truth be told, for these, we could just be going to the table. So yeah, for 99% confidence, we can just go to the table, and we see the critical value is 2.576. Now for 99.5%, we can do the same thing, and when we do that, we get a critical value of 2.807. So one thing you should hopefully notice as the confidence level increases is that the critical value Z sub C increases as well. So that's what will happen. So sampling error, it's the difference between the point estimate and the actual population parameter value. So for mu, the sampling error is the difference, sample mean minus mu. Now, our mu, the population mean, is generally unknown. We don't really know what that's going to be. So that's why we do all this stuff with hypothesis testing and confidence intervals. And of course, the sample mean does vary from sample to sample. So what happens is the margin of error is the greatest possible distance between the point estimate and the value of the parameter. And it is denoted by E, and it is this simple formula here, the critical value times the standard deviation divided by the square root of the sample size, which, if you remember properly, this is from the central limit theorem. It's back. So, conditions. Now, so the reason the sample does have to be random. That's a given. And the population itself has to be normally distributed, or that the sample size is greater than or equal to 30. Now, generally these conditions are pretty well defined, and I am actually in these videos going to show you what happens if conditions are not necessarily met. Now, generally in the we just kind of assume that the conditions are going to be met. But here, we're just, I'm actually going to take a little bit more time and show you how this works. So, using the data from the grocery store employees and a 95% confidence level. 95% confidence, so what this means is our critical value for Z, if we look at 95%, it is going to be 1.96. So, the margin of error is going to be, your critical value times standard deviation over the square root of the sample size. Now, if I remember, the sample size was, I believe, 40. Let me go back up to that real quick. Yeah, it was 40. So, what we're going to do, all you got to do is just punch this up, 1.96 times, let's see, population standard deviation is 7.9. And this will be divided by the square root of 40. So what we'll do is we'll take the calculation and figure that out. Let's see what we get. 1.96 times 7.9 over the square root of 40. And what we get is 2.45. So that's what our margin of error is going to be. 2.45 hours. So, that's how we're going to figure that out. So, using the data from, we have another problem that we're going to look at here a little bit later on. Video terminals, where we want the 95% confidence. We're going to find the margin of error for this mean. So we're going to assume the population standard deviation. Right now, we're going to be working with population standard deviation. That's also going to change a little later on in this course when we get into the t-distribution. So we're going to assume the population standard deviation. Now, I didn't give you a sample size. It is going to be 20. So the margin of error. Now, by the way, let me go back up a little bit. So technically, this should be 2.5 hours because if you recall, the sample mean was 29.6. And so if the sample mean and standard deviation are to 1 decimal place, the margin of error should go to that as well. So for this one, our population standard deviation is 36. Now we're using 1.96, of course, and it'll be times 36 over the square root of 20. So if I go to the calculator and try to figure that out real quick, divided by the square root of 20, we get 15.78. Now, why I rounded that to 2 decimal places is simply because our sample mean was 2 decimal places as well. And why is this pen picking this time to do this to me right now? So yeah, 15.78. So that's going to match up with that very nicely. All right, so I'm going to go ahead and end this video, and I'm going to come back and work on the next one. So I hope you enjoyed it. All right, welcome back, everybody. So this is video 2, part 2 of Unit 4 and 5 video. So where we left off was we wanted to figure out the margin of error for the video terminal problem, and that was on page number 4. So we got our margin of error of 15.78, and it's going to be in millivolts. So that's what we get for that. Now, just an interesting thing is if you've ever taken AP statistics, this is a very generalized formula here. So the statistic, which has been x bar, it's equal to critical, it's plus or minus the critical value, which has been our z sub c, and our standard deviation, which is sigma over the square root of n. So we're also going to be getting into t-intervals in a little bit, but for now, we're just going to stick with all the z-interval stuff. So a confidence interval for the population mean mu, it's from the point estimate minus your margin of error to point estimate plus your margin of error. And the probability at the confidence interval containing mu is C, assuming we repeat this estimation process a large number of times. So the conditions or requirements, we have to verify that the population standard deviation is known. Now, if you don't have that, or you have a sample standard deviation, or you have no standard deviation, what you'd have to do is you would be using the t-interval. Now, we're going to get into all that at another point in time. But for now, so we need to find, so the sample has to be random, the population itself is normally distributed, or that our sample size is greater than or equal to 30. So we need to find our sample statistics, find the critical value, margin of error, the left and right endpoints, and then you interpret. So with 95% confidence, we could say the population mean number of friends is between this and this. And we can always draw pictures to help us out. So what can we say about a confidence interval? So interpretation is one of the things that you are going to be expected to do whenever you do these confidence intervals. Now, there's a right way to interpret them, and there's a wrong way to interpret. So some of these things you may say, like, if this study were repeated or conducted many, many times, I expect, whatever the context, or this is my favorite one. Based on a sample of size n, we are C% confident that the true proportion, mean or proportion, is captured within the interval from this to that. And make sure it's in context. So that's the other big thing. Make sure it's in context. So some of the things you cannot say, things you may not say, or the 7 things we can't say on TV, homage to the late great George Carlin. Population mean is between low and high 90% of the time. It's either in or it's not. Or there's 90% probability that the actual mean is in the interval. That's another way. Basically, this is always my favorite way to interpret a confidence interval. This is how I'm going to interpret them. Basically, yeah, it's a canned statement. What I mean by a canned statement, if you ever go on a job interview, you probably have canned statements to standard job interview questions like, where do you see yourself in 5 years? You probably know, you probably should expect to know what to do. So yeah, this is another canned statement, so to speak. So, the way confidence interval works here is these confidence intervals all appear to be the same size. There are different samples. Now, in the long run, 9 out of every 10 such intervals will contain mu. And yeah, there's one that doesn't. So, a college admissions director wishes to estimate the mean age of all students currently enrolled. So, in a random sample of 20 students, so there's requirement 1 that the sample is random, and the mean age is found to be 22.9 years. So, from past studies, the standard deviation is known to be 1.5 years. And I should have made it a little bit clearer that it is population standard deviation. And the other thing is the population is normally distributed. Now, I am not going to make you do this, but the conditions have been met. I'm not going to make you point out the conditions, but I am going to point out the conditions myself. And I'm going to show you what happens whenever the conditions are not met. So, the mean age is found to be 22.9. The standard deviation, population standard deviation, is 1.5, and our sample size is 20. So, our critical value, since we want a 90% confidence, we look at 90%, and it is 1.645. Now, since the mean and standard deviation are simplified to 1 decimal place, what we're going to do with that is we're going to round our margin of error to 1 decimal place. So 1.645 times 1.5 over the square root of 20. Now, I will tell you whether or not I want more places. Times 1.5 over the square root of 20, and that will be, we can call it 0.6. Technically, Yeah, we'll call it, 0.55, but it really is zero point 0.6 to 1 decimal place. So our confidence interval is going to go from 22.9 plus or minus 0.6. So what we get here, we add and subtract 0.6, and we get 22.3 to 23.5. And so there's our confidence interval. Now, the other thing is we now have to interpret. That is the big thing. And it's just one sentence. And I can actually type this. So, based on a sample size of 20 college students, we are 90% confident that the mean age of all currently enrolled college students is captured within the interval from 22.3 to 23.5 years of age. And that's all I really need. So that's not too bad. I'm going to kind of make that a little bit bigger so that you can see it, and that's what it is. And so that's basically what I need you to do for interpreting a confidence interval. Now, interpreting, so here's the thing. So you're probably thinking, wait a second, we know nothing about a population mean. Why would we know anything about a population standard deviation? Well, truth be told, we shouldn't. But I'm trying to keep the calculations as simple as possible. Now, here's an interesting thing. So if you go to the calculator, now, if you go to stat and you're going to pick tests, we're going to do a Z interval, and whether it's for data or stats, we're going to have it for stats. Now, our standard deviation was supposed to be 1.5. Our sample mean was 22.9, and we had a sample of 20 students. Our confidence level was 0.9, and if we calculate that, here it is. So, yeah, that's exactly what we get here. So, I thought that this was pretty cool. You'll be able to do that for this to check your work. Now, of course, the confidence intervals will not interpret them for you, but this calculator can't do everything for you. So the reason we're doing the confidence intervals for the mean, where we know the population standard deviation, the reason we're doing that, we are trying to keep, I'm keeping the calculations as simple as possible. This is the basic, these are the basics of confidence intervals. Things are going to change a bit, a little bit later on in our unit. But for now, we're going to keep it nice and simple here. We are going to be doing confidence intervals for means when the population standard deviation is in fact unknown, but we're not going to do that just now. Now, we're going to go on to page 7 here, talking about how confidence intervals are one of the two most common types of statistical inference. Whenever we want to estimate a population parameter, get an estimate of it, confidence intervals are great for that. So what will happen now is we're now going to get into significance or hypothesis testing, and that'll have a different goal: to assess the evidence provided by data about a claim. So what we're going to be doing here is you're going to be determining a claim based on how the problem is written, and we're going to come up with evidence, that's our calculations, to determine whether to support or dispute our claim. So, for instance, an automobile manufacturer advertises that its new hybrid car has a mean mileage of 50 miles per gallon. So, to test this claim, what you would do is you would take a sample. If it differs enough from the advertised mean, you can decide that the advertisement is false. So, this significance test is a more formal procedure for comparing observed data with a claim, also called a hypothesis. It's a statement about a parameter such as population or mean. We're going to be dealing with means here and only means for the time being. And we express the result of a significance test in terms of a probability that measures how well the data and the claim agree. So we're going to learn the underlying logic of statistical tests, how to perform tests, and about all this, and how they're connected to confidence intervals. So a hypothesis is a claim about a parameter. We have to carefully state a pair of hypotheses. One will represent the claim and the other will be its complement. And when one of these is false, the other has to be true. So the null hypothesis is a statement of equality such as less than or equal to, or greater than or equal to. It's denoted as h sub 0 and read as h sub 0 or h naught. The alternative is a statement of inequality. That has to be true if the null is false. And that is denoted h sub a. Also can be denoted as h sub 1 as it's also denoted as h sub 1 in other books. So if you're looking at any other material, you'll see h sub 1. So that's what we'll get there. So to write the null and alternative hypotheses, translate the claim made about the population parameter from a verbal statement to a mathematical statement. Depending on whether it is two or one-sided, we can write either the null or alternative hypothesis first. Then we write its complement. So, in these cases, these are one-sided tests. And what we do here is, in this case, this would be a right-tailed, where it is greater than the claimed value, and this would be a left-tailed test. We're going to see the pictures and drawings of it in just a little bit. But we can also write the null. Some books will just simply write the null as mu equal to something. So basically, right off the bat, we are assuming equality. Even though it is written like this is still equal to. We're assuming equality here. We're assuming that the null is true. So let's think about this. Hopefully you'll never have to be in a court of law, but our general statement is innocent until proven guilty. So yeah, what we're doing here is we're assuming the null to be true, and what we're doing here, presumption of, so it's basically equivalent to saying it's a presumption of innocence. It's a legal principle. It's actually, it just basically comes from English common law, that you are innocent until proven guilty. The null is true unless we have evidence to find otherwise. Now, and here's the other thing. If we find evidence against the null, does that necessarily mean it's true? Or does that mean we would, it means we would reject the null based on our calculations. But where I was going with that was, we would reject the null based on our calculations, but is that necessarily the absolute final truth? No. Again, it's based on evidence. You can always talk, give you an example. The Casey Anthony murder trial, which happened, I think a lot of you probably would remember that. They found her not guilty of the crime of murder in the first degree, simply because they just did not have the evidence to find her guilty of the murder. Now, if they had gone for manslaughter, I think they would have been able to get her, but on murder one, that was a very slippery slope. So, regardless of your opinion, that's kind of how hypothesis testing works. We're always assuming the null to be true. If you ever watched Cops, I used to love watching Cops. I still watch old reruns of it. The disclaimer at the start is, all suspects are innocent until proven guilty in a court of law. So yeah, again, always have to assume the null to be true. Hopefully you won't ever have to deal with the law, because as the Bobby Fuller Force say, you'll fight the law. I fought the law and the law won. Alright, so for these ones, we're on page 8 now, writing the claim as a mathematical sentence. So a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. And we're going to write the hypotheses. So if you remember, the null is always a statement of equality. So proportion is 0.61. So the alternative would be the proportion not equal to 0.61. So in this case, this first one is our claim. So that's going to be the claim for that one. Alright, so for the second example here, a car dealership will announce that a mean time for an oil change is less than 15 minutes. So for the null and for the alternative, we're back to means. And it's going to be 15 on each side. And we can use minutes or not. I'm just going to write these, as minutes. So since it's less than, that's what the alternative hypothesis is going to be. And that is our claim. So it would follow that based on this, the complement of less than is greater than or equal to. But I would gladly accept this. I would gladly accept that. So do not freak out there. Now, not to say my lab will want greater than or equal to. The reason I accept it this way is basically it's a statement of equality. We're really just trying to prove it in one direction here. So a company advertises the mean life of its furnaces is more than 18 years. So there's our null and alternative, 18. And since it's more than, it's going to be that, and that will be our claim. So one thing that you've noticed is, depending on the situation, either the null or the alternative could be the claim. Now, the null hypothesis would be less than or equal to, or equal to 18. Mean life of furnaces is greater than 18 years. Well, I hope that's the case with mine. Mine is 10. My parents have a 40-year-old furnace. So, no matter which hypothesis test or which hypothesis represents our claim, you always have to begin the hypothesis test assuming the equality condition in the null is true. And so at the end of the test, one of the two decisions will be made. We'll either reject or fail to reject. Now, another thing is, we will never, ever accept null. You never want to accept the null. We fail to reject it. And basically what that means is, we don't accept it. We just have evidence against the alternative. We have evidence that, the alternative hypothesis is not true. So, and it's just like, when you find, accepting the null, failing to reject the null means you found them not guilty. Now, that doesn't necessarily mean someone is not guilty. I mean, it's not guilty of the crime against them. It doesn't mean that whether they did or didn't do it. They're just finding you guilty or not guilty of the crime based on evidence. So based on evidence, we just fail to reject the null, and that's how it works. So I talked about a type 1 error, and that happens when you reject a null when it is actually true. The symbol alpha, yep, we're going to start getting into some more Greek letters. It's used to represent the probability of a type 1 error. So type 1 error is where we rejected the null incorrectly. Now, a type 2 error is where we fail to reject the null when it is actually false. And the symbol beta is used to represent the probability of a type 2 error. We're never going to actually have to calculate that, but that's how it'll work. So, one thing, I would definitely write this on your formula sheet. The truth about the population. If you rejected the null and it was really true, you committed a type 1 error. If you failed to reject the null and the null were actually false, that is a type 2 error. And so, you think about this, let's say the truth is that they are guilty and, not guilty. Let's say, we know somebody is, whether they're guilty or not. So if we rejected the null, what we did was, the null is true. Oh, other way around, I'm sorry. Not guilty. And otherwise it could be guilty. So if we rejected the null, we found them guilty. If we failed to reject the null, we're finding them not guilty. And so you can see why you can see the equivalence here. So the USDA limit for salmonella contamination for chicken is 20%. A meat inspector reports that the chicken produced by a company exceeds the USDA limit. You're going to perform a hypothesis test to determine whether that meat inspector's claim is true. Well, when will a type 1 or 2 error occur, and what is more serious? So let's think about this here. So USDA limit for salmonella contamination, we're going to perform a hypothesis test to see whether the meat inspector's claim is in fact true. So here's the null and here is the alternative. So it exceeds the USDA limit, so the proportion of bad chicken is greater than 20%. So the null would be less than or equal to 0.20, or we could accept that the proportion is just equal to 0.20. So it could work that way as well. So what happens here is a type 1 or type 2 error. So if we did a type 1 error, where a type 1 error, what happens here, if you remember, is you rejected the null, but it was really true. So, and you will be expected to tell me type 1 or type 2 errors for one of your problems when you take the test. So we rejected the null, but it was true. Now, that's not enough. What I'm going to ask you for is a type 1 and type 2 error in the context of the problem. So what happened is we believed the chicken was bad. Now, if we rejected the null, that means we went with the alternative. So if we went with the alternative, yeah, so we believed that the chicken was bad, but since the null is true, it really was not. So, a type 2 error, where we failed to reject the null. So in this case, we failed to reject the null. That is, we went against the alternative. And since we went against the alternative, we believed the chicken was acceptable. But it really was not. So what do you think is more serious and why? Well, I definitely think a type 2 is more serious. Yeah, a type 1, if we committed a type 1 error, we believed the chicken was bad, so we wasted good chicken. So we wasted perfectly good chicken. For a type 2, we served bad chicken. So I definitely think a type 2 error is much worse in the whole grand scheme of this. So level of significance is your maximum allowable probability of making a type 1 error. Now, it is denoted by alpha, and we set the level of significance to a small value so that we want the probability of rejecting a true to be small. So the alternative hypothesis is one-sided if it states that a parameter is larger or smaller than the null. And it's two-sided if it's different. So, we're going to learn why we do one and two-sided tests. There is some practicality for two-sided tests, but most of it in the real world is simply going to be one-sided or one-tailed test. So again, now by the way, never write a hypothesis about a sample statistic. So that's one thing that you need to realize. It always is about the parameter. So again, you always assume that the null is true. So at the end, one of two decisions are going to be made. So one of the two decisions, you would either reject the null or you would fail to reject the null. And so because your decision is in fact based on a sample, there definitely is a possibility of making a wrong decision. It can happen. So, that's why we have the type 1 and type 2 error. Again, we're making our decision based on a sample. So, that's why it works this way. So, some more about hypothesis tests. After we state the null and alternative and specify the level of significance, a random sample is taken from the population and sample statistics are calculated, and we compare it with the parameter called our test statistic. Now, since we're going to be dealing with means for the time being, the test statistic is X bar, and the standardized test statistic, well, in this case, it's going to be Z. Now, a little bit later on, we're going to be dealing with T. Now, for proportions, we're going to have this. Now, for standard deviations and variances, we don't do these. But, in case you're ever curious, you can do hypothesis testing about that. So this p-value that we speak of is the probability of getting a value of the test statistic at least as extreme as the one representing the sample, assuming the null is true. So what happens is, we're assuming that the null is true. This p-value is not the probability of the null or alternative. So it is the p-value or the probability that we get something as extreme as we did based on the claimed mean. And so if the p-value is lower than our alpha value, we would reject the null. So generally, the alpha level is going to be 0.05, and I will always give you an alpha value. So we can reject it based on different alpha levels. So let's say our p-value for a hypothesis test was calculated to be 0.0234. We could actually calculate that based on the normal distribution. It's not 99% of the time, it is 100% of the time. So what does choosing our alpha do? We're going to talk about that shortly. So if the p-value was 0.0234, if alpha was 0.05, we'd reject it, but if alpha was 0.01, in that case, we would fail to reject it. And a good saying for this is, if p is low, then the hoe must go. So the p-value, again, assuming, it is the probability, assuming the null to be true, of obtaining a sample statistic as extreme, and depends on the nature of the test, and the p-value is indicated by the alternative hypothesis. Now, it is not the probability of either hypothesis. It is not the probability of the alternative hypothesis. A lot of people misconstrue that whole thing. So the tails are bounded by critical values. We're going to see how critical value and p-value all work together. So decision rule based on p-value, for instance, if the p-value is 0.0237, in this case, if alpha was 0.05, we would reject the null. And if alpha was 0.01, we would fail to reject the null in that case. So that's what we would get. So left-tailed and right-tailed and two-tailed, this is how it all works. So for each claim, so we've already kind of done this. So the null hypothesis is that p equals 0.61. The alternative is that it is different from 0.61. So what we want to do is see if it's different. So what happens here is we would have to get, now for proportions, we would still be getting a t statistic. So basically, the rejection region, there's actually two rejection regions. So what happens is when we calculate our test statistic, which for the time being is going to be z until we get to the t, we would be rejecting the null if our z statistic, remember, in the middle, z is always 0. And here is where we would fail to reject. And of course, if you remember, the null is your claim. So a car dealership announces that the mean time for an oil change is less than 15 minutes. So, greater than or equal to 15. So what happens here is, since it is less than, our alternative is less than, this is the rejection region. And in this case, we have the fail to reject region. And then lastly, oh, and by the way, the claim was the alternative in this case, and the claim is going to be the alternative for this one. Alternative is that it is lasting longer than 18 years. The null is that it is less than or equal to 18. So what happens here is we have our rejection region here. Otherwise, you would fail to reject the null. So we're going to determine some critical values and all that for this, and that's probably where I will, this is definitely where I'm going to end the video after this. So, the rejection region or critical region, you can read through all that. So, we're also going to be able to determine p-values based on these. So, the null hypothesis, since this is left-tailed, we don't really have something, it's, whatever it is, it's less than something. And so, if I actually go back up here real quick, if you look, the alternative hypothesis, if it's not equal to, obviously it's two-tailed. If it is less than, it's left-tailed. If it's greater than, it's right-tailed. So, if we, the null hypothesis, we don't really know what that is. So, what we've actually done here is figured out our test statistic of negative 2.23. So, here is negative 2.23. Now, if our alpha value is 0.01, then, so depending on what the p-value is. So, the p-value, we would get back into the normal CDF from negative 10 to negative 2.23. So, in doing that, normal CDF from negative 10 or negative 100 to negative 2.23, we get 0.0128. So, this area that is in red happens to be 0.0128. Now, since our p-value was below alpha, greater than alpha, 0.0128 is greater than alpha, we'd fail to reject the null. So, another way we can do this, I'm actually going to draw a second curve here. Now, since our alpha value was in fact 0.01 and left-tailed, what we need to do here is we need to figure out the critical value, knowing that this is an area of 0.01. We know that that area is going to be 0.01. So all we have to do is inverse norm that of 0.01. If we do that, we get a critical z value of negative 2.326. Now, here's the thing. Uh, since our critical value, if we did the, we make the same conclusion whether we do it with p-value or critical value. What happens here is, if we did this with critical value, this region that is mixed would be our rejection region. But, or you can look at it this way. If we put the rejection regions in blue for either one of these, now the actual Z was outside of them. So that's just extra evidence that, yeah, you would fail to reject the null. Again, it's the same exact conclusion whether you use the critical value or p-value method. I'm going to go with both of these, so that's how it'll work. But if you go to, since this is one tail, area in one tail of 0.01, and again, large degrees of freedom, 2.326, well, since it's left-tailed, you take the negative version of it, and that is what you get. All right, so we have a test statistic for this of 2.14. So what happens here is we need to, so our Z is 2.14. So what we have to do here, I know this is probably a really crappy looking curve, but so be it. So the p-value, we actually have to multiply this by 2. From 2.14 to 10, and so in that case, it's 2 times normal CDF, 2.14 to 10, and we get 0.0324. Now, what happens is, since this is less than, since the p-value is less than alpha, what we do in this case is reject the null. So if p is low, the hoe must go. Now, I'm going to draw a curve here pointing out the rejection regions. Now, let me reiterate something here. So this is a very lousy looking curve, but we'll deal with it. So yeah, negative 2.14. Of course, we could have found this area and multiplied it by 2. Now, what we're really looking at here, we need a rejection region since our alpha is 0.05. The area is going to be 0.05 in each of these. So what we can do is, if we have a two-tailed area of 0.05 or a one-tailed area of 0.025, we see a critical Z value of positive and negative 1.96. Now, since our p-value, our actual Z value was this, it was in the rejection region, so it's just additional evidence that you in fact will reject the null. Alright, so for this last one, we're going to find the p-value for a right-tailed hypothesis test of Z equal to 2.75. So, and since it's right-tailed, we want it to be greater than that. So for the p-value, we would simply normal CDF from 2.75 to a large number. And what we get here is 0.003. So since the P is very low, you're going to reject the null. So we reject the null. Now, if I wanted the one-tailed value, one-tailed area of 0.05, and so if I look here, one tail 0.05, it is 1.645. So this Z value would have to be 1.645. And so since that's in our rejection region, we would reject the null. All right, so that wraps up video number 2. So I hope you enjoyed, and we will get back to it later. Take care. All right, everybody, welcome back here. So where we left off was on page 15, determining critical value, finding the p-value. So what we're going to do now is, we are going to start here on page 16, and what we're going to do is what we're going to go ahead and do here is we're going to go ahead and start carrying out hypothesis tests as well as confidence intervals, and hopefully we'll also start seeing some connections between the two in this section. So the z-test for a sample mean mu can be used whenever the sample is random and the population is normally distributed, or for any population where the sample size is at least 30. So the test statistic is the sample mean x bar. The standardized test statistic is z, where sigma, the population standard deviation, is known to us. Now, in the real world, that's not going to be the case, but again, I want to go through the basics of this before we actually get into the t-distribution. So the population standard deviation has to be known, and the sample is random, and that the population is normally distributed, or that n is greater than or equal to 30. So we have to state the claim mathematically and verbally, identify your null and alternative hypotheses, determine the level of significance, find the standardized test statistic, find the area that corresponds to z. Now we're also going to use the critical value as well. So the purpose of the critical value is that is going to give us a sort of just an extra confirmation, so to speak. So we find the p-value, make your decision to reject or fail to reject. Now again, you never want to accept the null hypothesis. Then lastly, we want to interpret the decision in the context of the problem. Now this test statistic is the statistic, which in our case is x bar. The parameter is mu, which is the claimed mean. So this formula here, standard deviation, this is a generalized AP formula, so that's where they get this. All right, so that's how we're going to do this. Now, what we're going to do is we are going to do hypothesis testing, and we're going to see, so I've already kind of rigged this up a bit. So a couple of the things is that the sample size is greater than or equal to 30, and it was randomly chosen. Now, population standard deviation is this. So in auto racing, this pit crew claims that its mean pit stop time is less than 13 seconds. So in addition, we're going to construct a 98% and a 99% confidence interval. We're going to see what that does. So for the null and alternative, it's claimed that it's going to be 13 seconds. And since it's less than, obviously this is our claim. So the null hypothesis would be greater than or equal to 13 or equals 13. So that's what we're going to get for that. Now, what we're going to do here is we're going to figure out what the z-score is. So the z-score is this. So what we can do here is we can punch this up in our calculator. Now, in case you're wondering how this is actually calculated, we have 12.9219 minus 13 over 0.19 over the square root of 32. So what we need to do here is figure this out. So if we set up this fraction here, just like so, we get 12.9219 minus 13 over, if we want to go ahead and set up another fraction, let's see, that would be 0.19, and that's going to be divided by the square root of 32. So what we're going to get here is negative 2.325. So that's what we're going to get for that. Negative 2.325. So, when we get that for the z-score, what we're going to do is, figure out the p-value. All right, so for the p-value, given that the alternative hypothesis was less than, we want negative 2.325. So what we would need to do is normal CDF from negative 10 to negative 2.325, and when we do that in our graphing calculator, what we get here is exactly 0.01. Now, well, technically it's not exact, but here's the thing. So it is actually like, you could say 0.01004. So technically what we would want to do is fail to reject the null, but notice that the p-value is right on the cusp. So that's going to come into play in just a couple of moments. Now, if we look here at an alpha value of 0.01 for area in one tail of 0.01, if we look at large, we get 2.326 for the critical value. Well, since this is a left-tailed test, the critical value and this z-value are dangerously close to each other. As a matter of fact, yeah, they are only off by 1/1000th. So what we see here is, the critical value matches the z-score we calculated. So basically, I would not give you one on a test like this because the p-value is right on the cusp. You are either going to reject the null or fail to reject the null. You're going to do one of the two. Now, Next thing I want to do here are the confidence intervals. Now, here's the thing. Our margin of error is equal to the critical value times standard deviation over the square root of the sample size. So this Z sub C simply depends on your confidence level. So what we're going to do here is we're going to round this to 4 decimal places because that's what our sample is. So if we do this for the 98% confidence, now the sample mean, if you remember, for confidence interval, it is the sample mean plus or minus your margin of error. So we have a 98% and a 99% confidence interval. So if we look at these, confidence level for 99, it is 2.576. And for 98%, what we would get is 2.326. So what I'm going to do here is, we're going to calculate this to 4 decimal places, and then we're going to add and subtract that from the mean in either case. So what we want to do here is, for the margin of error, we get 2.326 times 0.19, because that is the standard deviation, and that is then divided by the square root of your sample size, which is in fact 32. So one thing I think I could actually do here is, I'm going to try to do it this way with the windows here. All right, so if we do this, 2.326 times 0.19, and that is then divided by the square root of 32. So to 4 decimal places, what we get here is 0.0781. Now the margin of error for this is 2.576 times 0.19 over the square root of 32. So if we want to figure that out, well, that's actually really easy to do. All we got to do is replace the 2.326 with 2.576. And we get 0.0865. So here's what happens. Our sample mean for this was 12.9219. So, 12.9219 plus or minus 0.0781. So if we punch that up on the calculator, minus 0.0781, 19 plus 0.0781, we get the confidence interval is going to be from 12.8438 to 13, which this is right on the money. Now, there is actually a connection here, and we're going to see that in just a few moments. But if we did 12.9, I don't want to do that here. I want to punch this up on the calculator. 12.9219 minus 0.0865, we get 12.8354 to 13.0084. Yeah, I know it's close to 13, but the thing is, it does include the 13. Now, here's the thing. You're probably thinking, now wait a second. If the alpha level was 0.01, now, why is it corresponding to 98% confidence? Well, if we take a look at the table here, our area and one tail, our critical value, yeah, it was 0.01. Well, no, we actually wanted it in one tail here. I'm sorry. That was area in one tail of 0.01, which does correspond to 98%. So that's what happens when we do this. Because this was one tail, this corresponded to a 98% confidence interval and not 99. Now, we're going to see something a little bit different when we get into the whole two-sided business here. So, now, the next thing I want to do is I actually want to show you how this could be calculated in the calculator. So if you want to do the hypothesis test, we're going to do a z-test. Now, we have stats to put in. Our claimed mean was 13 seconds. Now, our population standard deviation was 0.19. Our sample mean was 12.9219 with a sample size of 32. Now, if we look up at our alternative hypothesis, it was less than. So what will happen here is we can actually calculate that, and what we see is we see exactly the same thing as we did. The z calculation and the p-value. Now, if we go back to z-test, we can even draw this if we want. And that's what we get when we draw this. Now, so this is a case where we wouldn't make a decision on this. And again, I would not give this one to you on a test. So just to let you know. Now, if you want to do the confidence interval, you can go to tests and choose z interval. And here's the nice thing. If you go to stats, what you see is everything is already there, except we got to just change the confidence level to 0.98. Whoop. I hit one more key than I really needed to. And let's see here. We go ahead and calculate that. 12.844 to 13. Yeah, see? So that's how the z interval gets calculated. If I want to just verify my 99% confidence interval, let's see what we get. 12.835 to 13.008. Yep. So that's how all that will work when we're doing, confidence intervals. Now, we're now going to change the things around a bit. So we already know that the hypothesis test, we already know that the alpha of 0.01 corresponds to a 98% confidence interval. So that's why we're only going to do 98% confidence intervals here. Now, the hypotheses do remain the same. However, I am going to write those out again. The mean is 13, and we still think it's less than for the alternative. So an alpha level of 0.01, we need to calculate the z-score, which is 12.8 minus 13. And truth be told, you could do this outright in the calculator, but I'm trying to show you where everything comes from. 0.19 over the square root of 32. So if I go to my calculator and do this, and we have 12.8 minus 13. And then it's divided by 0.19 over the square root of 32. And what we get here is a z-score of negative 5.955. So, if I go ahead and do this on the, if I draw this out, negative 5.955, for the p-value, we would normal CDF from negative 10 to negative 5.955. And what we're going to get here is, I think we're going to get a very small p-value. So if we normal CDF, this time it's negative 5.955, and we get 1.3 times 10 to the negative 9. Or basically 0.00000013. But for all intents and purposes, we can just say this p-value is in fact 0. Now, so what happens here is based on this, based on the p-value of 0, you reject the null. So, and let me explain to you also real quick. So what does this p-value mean in the context? Well, what this p-value means in straight up context is the probability, I didn't want to do it that way. Yeah, let's see. Probability that we get a sample mean of 12.8 seconds based on the fact, given that the true mean population pit stop time is 13 seconds, is 0. Okay, I don't know why my computer is doing this all of a sudden. Okay, hang on. Why is my computer? Let me get this back up here. Oh, I was hitting the wrong thing. Okay, so there's no chance of this happening. So we already said we reject the null. Now, the thing is, we want to reject the null in the context of the problem. We don't just want to say, okay, reject the null or fail to reject the null. So what happens is, since we rejected the null, we have evidence suggest that the mean population mean pit stop time is actually below 13 seconds. Now, we're not saying that it is below 13 seconds. We're saying we have evidence based on that. So, we have evidence. Again, we're not saying, okay, this is it, end of story, you're done. No, what we're saying is we have evidence to suggest this. Now, before I go on to, the confidence interval, if you remember, the critical value for area in one tail was 2.326. So here's the thing. Since this is left tail, the critical is negative 2.326. So what happens here is, since it falls below that we're in our rejection region. Now, here's the thing. We're going to do the 98% confidence interval based on this. But wait, here's the neat thing. 98% confidence, our sample mean was the only one that changed. Our margin of error is going to remain the same. So our margin of error nicely remains the same. And our margin of error is going to be 0.0781. So if we have the sample mean plus or minus your margin of error, what that will mean for us is actually really simple. All we have to do is take 12.8 plus or minus 0.0781. And what we get out of that, for the margin, given our margin of error is what it is, our confidence interval goes from 12.7219 to 12.8781 seconds. So I'm going to just kind of type this out now. So let's see what we get here. Based on a sample of 32 pit times, we are 98% confident that the interval from 12.7219 seconds to 12.8781 seconds captures the true population mean pit stop time. So that's what we're going to get for that. Now I'm going to highlight this. No, I don't want to do that. And well, actually, I'm just going to highlight it this way because we're getting kind of into that. So that's how the confidence interval is going to work for this. Now, the next thing here is, if you notice, 13 is our claimed mean. 13 is way out here. Well, it's not way out here. It's either just out here or not. So the entire confidence interval is below 13 seconds. So what that should do is that should just give you further evidence that, hey, that claim of 13, less than 13, we have evidence to support that claim. Now, so for this last part here, let's go ahead and check our hypotheses with the calculator. So if we do a z-test, and now it's going to be 12.8. Calculate that. See, we get that. And if we go ahead and do the z-interval for that, now remember, it's 98%. Make sure you're entering that confidence level properly. I always do that because I'm so used to using my Inspire. It's a little bit different, which is fine. We get, see, the entire confidence interval lies below 13 seconds. All right, so now that's going to bring us to this next part of, we're going to change the sample mean yet again. Now you're probably thinking, my God, Mr. Jarrett, why are we doing this? I have a reason for everything I do. The hypotheses are going to stay the same. So if we want to calculate the z-score, this time we have a sample mean of 12.95. So if I want to go ahead and calculate that z-score for this, we get negative 1.489. Let's just call it that. So if we want to figure out the p-value, here is negative 1.489. The alpha is still 0.01. So if we want to figure out the p-value, we would just do normal CDF from negative 10 to negative 1.489. And let's see what we get when we do that. We get 0.0683 or 0.0682. So what happens here now, oh, by the way, so the critical value is still negative 2.326. This time, this critical value is here. So basically, this blue region would be our rejection region. We're beyond that. So in either event, what you should probably notice is, based on our p-value of 0.0682, we fail to reject the null. Now, that doesn't mean we accept it. We think, okay, the mean is going to be greater than 13 seconds. Instead, the way we would approach something like this is we have evidence to dispute the claim that the population pit stop time is below 13 seconds. And again, we have evidence to dispute the claim. We're not saying it is or it isn't. Again, we have evidence. So, p-value is higher. So since the p-value is high, we fail to reject the null. And make sure that you state it in the context of the problem. So, now since we did reject that, we failed to reject the null. Now, if we do the 98% confidence interval, this time it is 12.95 plus or minus, what was our margin of error, 0.0781. So if we go ahead and do that real quick, 12.95 minus 0.0781 plus 0.0781. What we get out of this deal is 12.8719 to 13.0281. So if you notice, in this case, our claimed value of 13, our claimed mean of 13, is contained. So that is just more evidence that we failed to reject the null. It's more of the same, really. You fail to reject the null. And if I wanted to interpret this, just write it out in one or two sentences based on a sample of 32 pit stop times, we are 98% confident that the interval from 12.8719 seconds to 13.0281 seconds captures the true population mean pit stop time. Now, That's all we needed to say here, and the reason we were able to just say, to just say this and be done, typically whenever we write out a confidence interval, we don't want to make a claim whether to fail or, reject or fail to reject the null. But if I go back to this p-value, the p-value of 0.0682 is the probability. And you don't have to write this out. What I'm trying to do is tell you what p-value means in the context. We get a sample mean of 12.95 seconds given the true population pit stop time is really 13 seconds. So this p-value is higher than our claimed alpha value. So that's why in this case we would fail to reject the null. So all right, so that's going to do it for this one here. So the next video we'll talk about two-sided, then we'll get into, I want to spread this out as much as possible. So I hope you enjoyed this. If you have any questions, ask. Take care. All right, so welcome back here. This is video number 4 for statistics. We're going to talk about some more hypothesis testing here. And in addition to that, we're going to start talking about the t-distribution. So that's what we're going to do here. So what we have for this one is, according to a study, the mean cost of weight loss surgery is $21,500. So you think this is incorrect, and you think it's actually different from this. So what that means here is this is going to be a two-sided test. And since the null statement is always that of equality, the mean is going to be $21,500, and for the alternative, it's going to be not equal to $21,500. So what we have is we have 25 surgery patients. Population standard deviation is $2,250, and the sample mean is going to be $20,618. So what we're going to do with that is calculate the z-score. Now, if depending on the side the z-score is on, whether if it's positive or negative, we're going to do a left or right-tailed test. But we'll multiply the p-value by 2 when it's all said and done. So what we're going to do here is we're going to figure out the z-score. So the z-score, if you remember, is sample mean minus the claim mean over standard deviation over the sample size. So we'll have 20,618 minus 21,500, and we're going to divide that by 2250 over the square root of 25. So that's what we're going to get for that. Okay, so when we enter this into the calculator, we are going to get a z-score of negative 49 over 25. Well, I'm going to multiply that. So what we get here is a z-score of negative 1.96. Now, since the z-score is negative, what we're going to do with that is we're going to do a left-tailed test. We're going to find the p-value when we do this. And what we'll do is we'll multiply that p-value times 2. So if we go ahead and do that, we'll just normal CDF from that to negative 1.96. So when we do that, we get a p-value of 0.02499, we multiply that by 2, basically we get a p-value of 0.049999. Now, so this is going to be, technically we would reject the null since the p-value is lower. But what would happen here in this case, this is where it's going to be right on the cusp. So what I want to do now, so we multiplied that p-value by 2 and got this. So technically we would still reject the null, but we're just, I'm not going to give you one like this on a quiz or a test or anything like that. So what we're going to do now is we're going to go ahead and find a 90% and a 95% confidence interval. So 90% confidence interval and a 95% confidence interval. So the critical z-value for each, that simply depends on the confidence level, 90 or 95. So for 90%, it's 1.645, and for 95%, it is 1.96. So the margin of error is going to differ between these two. So the margin of error is the critical value. Let's make sure we have that formula right. I know we do, but it is the critical z-value times standard deviation over the square root of the sample size. So 1.645, and we multiply that by, what was that standard deviation? 2250. 2250 over square root of 25. So for this, for the margin of error, and we're going to round this to the nearest dollar, 1.645 times 2250 dividing it by the square root of 25, we're going to get a margin of error of $740. Now for this one, the margin of error, 1.96 times 2250 over the square root of 25. So in my calculator, we calculate that again. Instead, so we get $882. So what we want to do is we need to take our sample mean plus or minus the margin of error. Now our sample mean was $20,618. $20,618 plus or minus 740. And for this, we would have 20,618 plus or minus 740 as well. All right, so when we want to do this, what we got to do is take the margin of error, so 20,618 minus and then plus 740. And so for this one, for the 90% confidence interval, we get 19,878 to 21,358. Now for this next one, wait, I already did 740. This should be 882. So what we get here, 19,736 to 21,500. So if you remember from the previous video, what you'll see is that on page 17, that the p-value was pretty much exact, and it corresponded, since our alpha was 0.01, it corresponded to a 98% confidence interval, not 99. Now for this This obviously corresponds to 95%. So we would have thought, wait a second, the alpha level was 0.05. Well, here's why. This is a two-sided confidence interval. So because the area in two tails was 0.05, we needed a 95% confidence interval. So an alpha value of 0.05, and since it's two-sided, it corresponds to a 95% confidence interval. 1 minus alpha. If it's a one-sided interval, it would correspond to 90%. All right, so we're going to do similar things here. So the purpose of doing that was to either, we had a p-value that was pretty much right on the cusp. So it depends on whether it's a one or two-sided. Now, whenever you get your questions or whatever, it will be clearly written whether it's one or two-sided. Well, I'm not going to say outright, but it'll be pretty clear, like you think that this is different, like, the cost could be higher or lower. There are a lot of medical applications particularly. So for this, a lot of the statistics are changing here. Well, not a lot of the statistics are changing actually. So for our null, mean is still 21,500. Alternatively, it is not equal to that. So the z-score is now 20,695 minus 21,500 divided by 2250 over the square root of 25. So if we go ahead and figure out the z-score for that, we get negative 1.789. So here, what that does for us is we want to figure out the p-value. So we have negative 1.789. We're going to end up multiplying that by 2 when it's all said and done. So we want a normal CDF to negative 1.789. And then we're going to multiply that by 2. So it goes to show the p-value will be 0.0736. So in this case, since the p-value is higher than alpha, we are going to fail to reject the null. So yeah, since our p-value of 0.0736, it is higher than 0.05, we fail to reject the null. And what that means is we don't accept it. Instead, we say we have evidence suggesting that the mean is not different from 21,500 significant. We should actually say not significantly different. So that's how all that's going to work. So if we want to do the 95% confidence interval, now here is the really nice thing. For the 95% confidence interval, our standard deviation and everything basically stayed the same. So all we have to do is we have to recall our margin of error, and that is $882. So we take 20,695 plus or minus $882. So what we get for this is 19,813 to $21,577. So if I asked you to interpret this, so based on a sample of 25 patient costs, we are 95% confident that the interval from 19,813 to $21,577 captures the true population mean cost of bariatric surgery. So that's our interpretation. Now, the thing is, 21,500 is contained within. And since it is contained within, that's just further evidence that we would fail to reject the null. All right, so for 2C, now we're going to change that. So the z-score is now going to be 20,195 minus 21,500, and we're going to divide that by 2250 over the square root of 25. So we want to calculate the z-score here, so if I punch this up in my calculator real quick, we get negative 2.9. So if the z-score is going to be negative 2.9, we want to figure out the p-value, and keep in mind we have to multiply it by 2. So using our wonderful Texas Instruments 84 Plus, we go here, normal CDF, and then we have negative 2.9 for the upper. And if we multiply that by 2, so the p-value is 0.0037. And my thing just went on. Oh, here we go. So yeah, the p-value is 0.0037. So, and if you remember, if p is low, then we reject the null. So, since our p-value of 0.0037 is below our alpha of 0.05, we reject the null. We have evidence that suggests the mean cost of bariatric surgery is different from $21,500. And I should also add the phrase significantly. So, and if you remember this p-value, the probability that we get a mean of $20,195 when the true population mean is 21,500 is 0.0037, which is our p-value. So that's what the p-value is all about. So now let's do that confidence interval one more time. Now in this case it is 20,195 plus or minus, it's still 95%, So it's plus or minus $882. So it's going to go from $19,313 to $21,077. Now, if you notice, the entire confidence interval is below 21,500. So based on a sample of 25 patients, or patient costs, we are 95% confident that the interval from 19,313 to $21,077 captures a true population mean cost of bariatric weight loss surgery. So that's the purpose of the confidence interval. Alright, so that's how we do confidence intervals and hypothesis testing when it comes to the standard normal distribution. However, if we don't know anything about the population standard deviation, which in all practicality, that's how it's going to be. So we have to use what we call the t-distribution that we met earlier with, we're going to actually introduce it. So this whole t-distribution, if you notice, there's degrees of freedom. Right now we've been using large. That's not the case anymore. So the degrees of freedom is n-1, which is simply 1 less than the sample size. So the t-distribution is what I like to call pseudo-normal. When the population standard deviation is unknown or sample size is less than 30, this is the best way to deal with a situation like this. So just like the z-distribution, mean, median, and mode are equal to 0, bell-shaped and symmetric, total area under this curve is 1 or 100%. Now, the difference is the tails are going to be a little bit thicker, and it's a family of curves that are determined by a parameter called the degrees of freedom. So it is just simply n-1. So it would be hard to see this in black and white, but what happens is the peak gets higher as the degrees of freedom increases and the tails get shorter. However, the tails are fatter. So basically, this the t-distribution gives us more room for error, so to speak. So we can use the table or we can use the calculator. So if we wanted to find 95% confidence, the critical t-value, if the sample size is 15, that means we have 14 degrees of freedom. So 14 degrees of freedom, and we want a 95% confidence, it's going to be 2.145, as we see right here. And we would see that on that table as well. Now, for this one, so I have the newest one. So if we were to inverse t, now 95% confidence, so 95%, that means it's an area of 0.975, and here's why. If we want 95% confidence, we want the middle 95%. And so if we want the middle 95%, that means there's 2.5% on each side. That means this is the 97.5 percentile. And if we were to inverse t on that with 14 degrees of freedom, we would get 2.145, just like the table. So if we standardize based on sample standard deviation, it's very similar, but it is different. There are much more area in the tails. Now, the purpose of this is we now have some more room. This is a more conservative estimate of things. So that's why we do this. It's a more conservative estimate. If we used a standard deviation provided by the normal distribution, that produces too many type 1 errors. Now, if you remember, a type 1 error was what was a type 1 error? Where we rejected a true null hypothesis. So we incorrectly rejected the null. So this one is going to smooth things out a bit. So Gossett found through research and a graduate degree in statistics found that using a standard error for the sample, the shape changed. Under his pseudonym, it's the student's t-distribution. So what happens here is, so that's the basics of the t-distribution. So I'm going to wrap this video up, and we're going to figure out the next part. I'm going to make the next video very soon, so enjoy. Have a good day. Alright, everybody, welcome back. I'm glad you're here. This is part 5 of this unit. I'm hoping to wrap this up in another video or two. I find it easier to make smaller videos because there's less possibility of them getting corrupted or something. So I talked about the t-distribution when the population standard deviation is unknown. So the t-distribution allows for more room of error, and we're going to talk about that using this example here on page 23. So what I've done here is I've gone ahead and put all 20 of these in my calculator. I'm going to go ahead and do a 1var stat on it on list 1. And so when we do that, we have a sample mean of 306.32 and such. So what I'm actually going to do here is I'm actually going to go ahead and paste this little screenshot right to this. So what we have to do now is calculate margins of error based on whether we do the normal distribution or the t-distribution. So if you remember, our margin of error formula is going to be either the critical z-value or now the critical t-value. So we're going to figure out these margins of error to 1 decimal place. So we're going to do this using z, and then we're going to do this using t. So we want 95% confidence. So what we can do here is, if we go to this 95% confidence, what we'll see is large degrees of freedom. So the critical z-value is in fact 1.96. And that's going to be equal to the population standard deviation, which they gave you, which in reality you really wouldn't know. But we'll we'll use this to 4 decimal places, 25.29, and no, that's 35.29, and that's going to be divided by the square root of 20. And using the calculator, what we're going to get for that to 1 decimal place will be 15.5. Now, actually, let's do that to 2 decimal places. So let's call that instead 15.47. So now let's do the same thing with t. So we have to do now, since the sample size is 20, we need to do 19 degrees of freedom. So 95% confidence with 19 degrees of freedom, that is going to be 2.093. So that's a little bit larger than the critical z value. And we'll use the sample standard deviation of 36.21, and we'll divide that by the square root of 20. So for this, we have 2.093 times 36.21 divided by the square root of 20. And for this now, we get 16.95, which, as you notice, is wider than the z-interval. Now, if we want to actually do the individual intervals, for the z-interval, all we do is take 336.32 and then plus or minus 15.47. So for this one, what we'll get is 290.85 to 321.79. Now, if we do the same thing with the t interval, we would have 336.32, in this case, plus or minus 16.95. So for this one, we have our bounds from 289.37 to 323.27. So it's obvious that the t interval is wider. It's a wider interval. Well, it's going to be wider because it's going to have a larger margin of error. Now, what would have happened here is, now since we know that for hypothesis tests, we can actually go by a confidence interval if we really wanted. Now, what we can do about that is actually really simple. What we can do is, let's say our claimed mean was, let's say our claim mean was 322, and we think it's lower. Well, for instance, so what would happen here is, in fact, I'm going to write this out. So, do this real quick. So, suppose we claimed that the mean tension was below 322 millivolts. According to the 95% confidence intervals, we would reject based on the z interval. However, we fail to reject based on the t interval. So, in other words, what happens here, if we rejected the null incorrectly, that's a type 1 error. And as I mentioned, a type 1 error is caused when we reject the null. This t distribution prevents us rejecting the null incorrectly. Now, if I were to actually go to the calculator, and why is my computer doing this? Okay, So if we were going to go to t interval, now actually let's do the z interval where we have the data. Now, if you notice here, it does ask for a standard deviation, for a population standard deviation. Now, in that case, it would be, we could just call it 35.29. And we want a 95% confidence interval. And what we see from the z interval is even though it actually gives you the sample standard deviation based on that, you would still be using the standard deviation that we entered. Now, here's something really interesting. So let's say we did the t interval now. Let's do the t interval for this, same information. And notice here, it does not ask you for the standard deviation. So what we do is we calculate that. And if I can just copy that over, or you could actually just view it on your screen or whatever. What we see here is for the t interval, yeah, we see that the calculations are in fact different. Now, if we actually wanted to carry out some hypothesis tests, we could actually do that now. If we go to tests and we do a z-test, if we input the data, now let's say we go with our claim of 322. And we think it's less, so if we calculate that, what we see is, we see that the p-value is smaller. Well, actually, wait a sec. So 95% confidence, since this is a one-sided test, our alpha value would actually have to be 0.025. I got a little crossed here, but an alpha value, so 95% confidence is 0.025 based on one-sided. So if we look here at the p-value that we got, we would be rejecting based on the z-test. Now, if we go to do the t-test, we would fail to reject. So, pretty cool how all that works. All right. All right, so yeah, that's how, so yeah, if we had done this with the t-test, we would be failing to reject the null. So, yeah, so basically, in other words, we have less possibility of making a type 1 error, so that's why we do the t-test. So now, we're going to find a critical value t sub 0 for a left-tailed test given alpha equal to 0.05 and n equal to 21. So what that means is then we have 20 degrees of freedom. So since it's left-tailed or one-tailed, we know that the t-value, the critical t-value, will be negative. So if we go to this table, 0.05, and how many degrees of freedom was that? That was 20 degrees of freedom. So one tail of 0.05 and 20 degrees of freedom was 1.725, but we have to go with the negative 1.725. Wait, what was that? I'm losing my train of thought. Yeah, so it's going to be negative 1.725. Now, one thing we can do is if we go to the graphing calculator and do an inverse t. So we go to distributions, inverse t. The area in this case will be 0.05 with 20 degrees of freedom. And yep, and we see it that way. Now, for a two-tailed test, given that alpha is 0.10 and n is 26, that means we have 25 degrees of freedom. So, basically an alpha of 0.10 means we have 5% inside each of these. So, in other words, one way to think about this would be it's equivalent to one tail with alpha equal to 0.05. So if we go to the two-tailed test with 0.10 and what was that, 25 degrees of freedom, 0.10 and 25 degrees of freedom, it would be 1.708. So basically, positive 1.708 and negative 1.708. So, and that's what we would use for the confidence interval, either positive or negative, doesn't really make a difference. Now, if we went by percentiles, this is the 5th percentile, this is the 95th percentile. Now, if we went to 25 degrees of freedom in either case, so 25 degrees of freedom, we get negative 1.708, and if we do that, we get positive 1.708. So that's what we're going to get for that. So now we can use the t-test for a mean, provided we don't know the population standard deviation. So this calculation is very similar, except we're going to use we're going to use sample standard deviation. So we've already seen the difference with what happens whether you use z or t. So we're going to put this all into practice now, but after that, here's what we're going to do. Did you know you can find the point estimate when given a confidence interval? You can also find the margin of error. So for example, let's say I have a confidence interval of 34.2 to 37.4. Now, point estimate is going to be in the middle, and that's going to be x bar. And since it's in the middle, all you have to do is take the average of those two. So if we simply took 34.2 and then 37.4, and then we divided that by 2, we get a point estimate of 35.8. Now, margin of error. Basically, what is the difference on each side? Well, 35.8 minus 34.2 would be 1.6. So if we go ahead and do some math on that, 35.8 minus 34.2, yeah, we get 1.6. Now, if we did 35.8 plus 1.6, we'd get 37.4, the other endpoint. Now, if we did this, 37.4 minus 34.2, that is the distance from end to end is 3.2. Half of that, half the distance, 1.6. So that's how finding the point estimate works. This is actually, I love to give a problem like this because it is so much easier than it ever looks. And I hope you'll see that. So what about finding the required sample size for a mean? Now, even though we just introduced the t-interval, we're going to have to use the z-interval here. Since we don't know a sample size, we're going to have to use the z-distribution here. So given the margin of error and standard deviation and needed confidence level, we're going to figure this out. So yeah, this is the formula that we're going to be using. And the big thing is you always have to round up. If you do not round up, for instance, even if you get, say, 307.01, the answer is going to have to be 308. Always round up, and I can't stress that more. So let's say we have a population standard deviation of 15. We want to know how many must be selected. Let's go within 5 IQ points. How many statistics students have to be randomly selected here? So our margin of error is going to be 5. Population standard deviation is going to be 15. So since we want 99% confidence, we go back to our little thing here, and it's going to be large, so 2.576. So our sample size is simply going to be 2.576 times 15 all over 5, and the whole thing gets squared. So using the graphing calculator, let's see what that is. And we get 59.72. So we need n to be 60. If you were to give me a decimal or something for this, you would be marked wrong. So, warning you now. And so for this next one, we're going to change a couple of things here. So let's say we want to be within 8 friends. We want to estimate the mean number of friends for all users of a website. And let's say we want to be within 8 friends of the mean. We have, let's assume the population standard deviation. Yeah, I know it's written as sample, but we have to do this with z. So, and 90% confident, well, 90% confidence corresponds to 1.645 times standard deviation of 59, and it is divided by 8. And squaring that, what we get here is 147.18, or we would actually have to use 148 for this. So when we do all this with proportions, we're going to see the same thing where you do have to round up. All right, so we're going to go to page 26 here, and we're going to do a hypothesis test about the mean with sample standard deviation given. Now, it doesn't say it here, but we have sample standard deviation of $1,842. So what we're going to do here is we're also going to see how this connects to confidence intervals. So for the null, used car dealer claims that the mean price of a 2-year-old sedan is at least $20,500. So the mean is greater than $20,500. The null would be just equal to that, or technically what we really want, or less than or equal to $20,500. So, actually, let me step back a bit here. So the mean is actually, so the alternative is actually going to be less than, because here's the thing. Even though it says at least, the fact that we have a mean that is lower, it should actually be this. Not equal to, just less than. So this could be greater than or equal to. Now, when you think about it, yeah, a car dealer is going to say that it is at least that, but we think it's less. I should have, and I will say this on a test that I give you, that I will say you think it's really less than this. So also we're going to do, so yeah, we have an alpha of 0.05. So since this is an alternative, since the alternative is less than, this is going to be a left-tailed test. So what we need to do here, instead of figuring out the z-score, we're going to figure out the t-score, which is basically everything we had from before. Now, with the exception that we're using a sample standard deviation here. So 19,662 minus 20,500, and we're going to divide that by 1,842 over the square root of 15. Now, by the way, since we have 15, that means we need degrees of freedom to be 14. So that's what we're going to get for that. So if we figure out this t-score, so in using my graphing calculator, I get a t-statistic of negative 1.762. So what we're going to do now is we're going to use that to find the p-value. So similar to the normal distribution, we have negative 1.762 as our t-value, and we want the area to the left of this. Now, in previous times, we would be using the normal CDF, but now we're going to use the t-CDF. So if we go back to our wonderful calculator, we're going to choose t-CDF. Now we have a lower, which we could do like negative 100 or whatever it is, and for the upper we'll have negative 1.762. Now the third parameter that you must enter is the degrees of freedom, which happens to be 14. And what we see here is a p-value that is just under 0.05. So we get a p-value of 0.0499. Basically, this is going to be just like the first example where we did on, let's see, this is page 26. The example that we're going to see this just like was on page 17. So right on the cusp. So yeah, the p-value for this is going to be right on the cusp. So I wouldn't give you one like this on a test. But what we're going to do here is now we're going to do the 90 and 95% confidence interval to see which one corresponds. Now, if you have if you've looked ahead, you'll see that in the next couple examples, I only ask for one different percentage. So if we do the 90% confidence interval, actually, let me step back a little bit, because one thing we can do here is if we go to stat on our calculator and we can choose a t-test. We have two sample, but we're not going to do that. Now, for this one, we're just going to use stats. So our claimed mean is going to be $20,500. Now, our sample mean is 19,662, and our sample standard deviation is 1,842 with a sample size of 15. If we go to calculate that, we see everything that we've had before. So what we're going to do now is see which confidence interval this more closely resonates with. So, for 90% and 95%. Now, the thing is, we have to consider our degrees of freedom, which happen to be 14. So, for 90% confidence and 14 degrees of freedom, we get a critical T of 1.761. And for 95% confidence, let's see what our critical T value is for this one, 2.145. So we're going to carry out the confidence interval calculation just like we did before. And it is true, I could just honestly do these in the calculator, but I do want to just show you how this all works. So for the margin of error, it'll be 1.761 times 1842 over the square root of 15. So what we want to do here is we do the math for that. And to the nearest dollar for this one, what we're going to get is $838. Now for this margin of error, we're going to do 2.145 times 1842 over the square root of 15. And we'll just round to the nearest dollar in this case. And what we'll get for this one is $1,021. So, just like before, what we need to do is take our sample mean plus or minus the margin of error in each case. Now, if you remember, the sample mean was, what was that, $19,662. So plus or minus 838, 19,662 plus or minus 1,021. So we're going to calculate the boundaries and see what happens. So what we see for these now are, for the 90% confidence interval, our alpha level was in fact 0.05. So one of those p-values was on the cusp. This confidence interval, the 90% confidence interval, was right on the cusp. So if we remember, this was a one-tail area in one tail of 0.05. Now if we look here, the area in one tail of 0.05 does correspond to a 90% confidence interval, just like with the z-tests. So this works for means exactly the same way, whether or not you use z or t. Because remember, if alpha is 0.05, but remember, it was one-tailed. And what that means is it corresponds to confidence level of 90%. Now, if you want to do these confidence intervals in the calculator, you go to Stat and you choose Tests. Let's go to T interval, and if we do the 90% interval, let's see, we get it right on the money, just like that. Of course, this is also very useful when you're doing MyLab. So, I actually had teased you a bit because I'd actually meant to say, well, no, I didn't mean to say 90%. I was hoping you were going to look forward and not cheat, but blow the example in class. So we want the 90% confidence interval here. So we're going to see what happens in the cases of each of these. So for this one, example TB, same hypotheses as before here. So for the null, the mean is equal to 20,500, and the alternative is that the mean is less than 20,500. So, by the way, I didn't formalize this in any way, but it does meet the conditions as they are random. It has to be a random sample. That's basically all it has to be, is a random sample. So we want to figure out the t statistic, which is 18,350 minus 20,500, and it's now going to be divided by 1,842 over the square root of 15. So we want to figure out what that is. All right, so for this one, we get a t-score of negative 4.521. Now, I think the p-value is going to be very low here. So here is negative 4.521. So if we want to figure out the p-value, we TCDF from negative 100 to negative 4.521 with 14 degrees of freedom. And when I do that in my calculator, so what we get for this is we get 2.4 times 10 to the negative 4. Basically, what happens here is, it is 0.00024. So, in that case, what we do is we reject the null. And since we reject the null, we go with the alternative. Evidence to suggest that the mean price is really below $20,500. Now, remember when we did hypothesis testing with critical value? Well, we can do the same exact thing here. If we go to a one-sided hypothesis test, or a one-sided or one-tailed test, area in one tail of 0.05 with 14 degrees of freedom, that's going to be 2.145. Area in one tail of 0.05. So the critical t-value would be negative 2.145. And since our actual t was less than that, that goes to show that we would, in fact, reject the null. Okay, I'm wrong. I looked at the wrong column. This online teaching is, looking at a screen all day isn't easy on the eyes here, but it should have actually been not 2.145 or not negative 2.145, but it should have been negative 1.761, which would match, which would not coincidentally, it matches the the confidence interval. So what we can do now is we can do the confidence interval. If we do the 90% confidence interval, the nice thing about that is for the 90% confidence interval, all we have to do is remember the margin of error, which was $838. So if the margin of error is $838, so what we do with that is we take this 18,350 plus or minus $838. 18,350 was our sample mean. And what we get here is 17,512 to $19,188. Now, if we want to interpret this, which I would expect you to, based on a sample of 15 randomly chosen used cars, we are 90% confident that the interval from 17,512 to 19,188 captures the true population mean used sedan cost. So, and the other thing is, if you notice, the entire confidence interval is below 20,500, which is the claimed value. So you could show this to a car dealer or whatever and say that. All right, so that's going to be that part. Now, if I want to go ahead and do the 90% confidence interval for this one, the T is 19,962. Let me just redo that. Let's see, 19,962 minus 20,500 over 1,842, dividing it by the square root of 15. Let's see what we get for the t-score for this one. We get negative 1.131. And so all we have to do here is we want to figure out the p-value, negative 1.131. So the p-value will be where we TCDF, and I'll just go ahead and do that right here on this calculator. So we'll have negative 1.131, and we get 0.1385. So we fail to reject the null. So when we fail to reject the null, remember, we're not accepting the null. All we are saying is, based on evidence, we fail to reject the null and have reason to go against the alternative that mean price of cars is not below $20,500. So that's what that's going to be. Now, if we do the confidence interval, I know I'm probably cutting some corners here. 90% confidence interval. All we have to do now is take 19,962 plus or minus 838. And what we get here is 19,124 to 20,800. So the claimed value of 20,500 lies within. All right, so since this video has gone on for 40 minutes, I'm going to stop it here. The next video will include these examples, and then we'll get into the material for proportions. So I hope you enjoyed this as much as I did. All right, so for this next video, we're going to start here on page 28, and we're going to change a couple of things. First off, instead of, we're going to have 31 water samples, we're going to have a sample mean of 6.749, sample mean pH. So an industrial company claims that the mean pH level of the water in a nearby river is 7, we think that it's different. Now, pH is a perfect two-sided example. For you chemists out there, you should know that if the pH is too low, that's acidic. If it's too high, then you're basic. Then you have a base. So you don't want the pH to be too far off from 7. So what you can do here is so this is going to be a two-sided test. The mean pH is going to equal 7, and for the alternative, the mean pH will not equal 7. So this is going to be a two-sided test. We have an alpha of 0.05. And since this is a two-sided hypothesis test, since alpha is 0.05, or so area in two tails is 0.05, we're going to correspond this to a 95% confidence interval. Yeah, let me just double check that again. So yeah, area in two tails is 0.05. So yeah, it's a 95% confidence interval. So the t statistic is going to be 6.749 minus 7 over 0.5784, and that's going to be divided by the square root of 31. Now keep in mind we have 30 degrees of freedom. So I'm going to figure that out real quick. So this t statistic is going to be negative 2.416. That's what we're going to get for this. So what we need to do now is find the p-value, corresponding to negative 2.416, and we have to multiply it by 2. And the reason we take the p-value times 2 is simply because this is a two-sided test. So yeah, p-value times 2. So if we TCDF what we need, so let's take a look here. TCDF to negative 2.416, this time with 30 degrees of freedom, and we want to multiply that by 2, so we get a p-value of, in fact, 0.022. So what do we do with that p-value? Well, what we need to do here is, since it is obviously less than alpha, so based on our p-value of 0.022, we reject the null hypothesis and have evidence to suggest that the mean pH in the river is different from 7, which is neutral water. Now, if you remember, this p-value of 0.022 that we get of 6.749 with assuming the true mean pH is 7 is 0.022. And that's how this works. So now we want to go ahead and figure out so we go with the alternative hypothesis. We have evidence to believe that it's different. So what we need to do here is we're going to do a 95% confidence interval. If we go ahead and do that, 95% confidence with area in two tails, well, 95% confidence, 30 degrees of freedom. So our critical TC value is 2.042. So 2.042, and what we need to do then is multiply that by 0.5784 over the square root of 31. And we're going to go ahead and do that real quick. So when we do that, we get a margin of error. Let's take that to 3 decimal places. So our margin of error is going to be 0.212. So for the confidence interval, we take 6.749 plus or minus 0.212. And what happens is 6.749 minus 0.212, we get the interval from 6.537 to 6.961. So if you notice, our claimed value of 7 is outside of this. So that's why that's further evident to reject the null. So if we were to interpret this, so let's interpret this based on a sample of 31 river samples. We are 95% confident that the interval from 6.537 to 6.961 captures the true population mean pH in the river. So that's how we would do the interpretation of our confidence interval. So yeah, this pH, if you remember, the pH needs to be 7. So what happens is, this is what we would be calling acid water. So, acid water is not good. So in our next example, we'll have a DMV. They claim that the mean wait time is 18 minutes. And we got a sample mean of 22.6. So, and I would write this probably a little bit clearer, but we have reason to think that the alternative, it's going to be the other direction here. So we think that it's going to be greater than 18. So our t statistic is going to be 22.6 minus 18 over 6.5 over the square root of 16. So, by the way, this is in fact 15 degrees of freedom. So, calculating that. So, in calculating this, what we get is a t-value of 2.831. So, that's going to be our t-statistic. So, our t-statistic, it will be 2.831. So, what we need to do is, so this is a right-tailed test. We finally have something a little bit different here. So, 2.831 is our t-statistic. So we would t-CDF from 2.831 to something big. And that means, and then we have 15 degrees of freedom. And this is a one-sided test. So what we would need to do here is, using the calculator, we t-CDF 2.831 to a big number, and we get a p-value of 0.0063. So what that means now is, since we have a p-value of 0.0063, what we would do here is we would reject the null. The null hypothesis based on our p-value of 0.0063. And what this means is, we reject the null, we have evidence to suggest the true population mean wait time at the DMV is over 18 minutes. Yeah, you can go to the DMV and end up basically waiting forever, which sucks, but what can you do about that? All right, so we're not going to worry about the confidence interval here, but I'm actually going to go ahead and punch this up in the calculator now. So if we go to tests and we do a t-test, we're just going to input stats. We have a population mean of 18, 22.6 for this, standard deviation of 6.5, and the sample size is 16. And this time we want the right tail, and we get exactly the same thing. So really there's no other choice here. No other way to express this here. The calculator is very simple. So that's going to help us down the line. Okay, so we're now going to go to the next value here. The next page, where we're going to find some p-values. Now, I know that probably seems really easy compared to what we've done here. But we're still going to do it anyway. So the test statistic, it's a left-tailed hypothesis test. We have n equal to 14, so that means we have 13 degrees of freedom. So we want negative 1.207 for this. And so to find the p-value, all we need to do is TCDF from like negative 100 to negative 1.207 with 13 degrees of freedom. And when we do that on our calculator, what we get for that p-value is 0.1245. So it's a pretty high p-value here. Now, so here's the thing. What I want to do here is, on the table, I want to look at 13 degrees of freedom here. And I want to keep in mind here, we need to take the positive version of this. So 13 degrees of freedom, and we need 1.207. We need the positive version here. Now, if you look here at we're dealing with area in one tail. Now, the purpose of this is what how I learned statistics back in my day, when I had to use the table to figure out a range of p-values here. So the 1.207 falls here. So what that means is area in one tail, it has to be greater than 0.10, and it is. So we're not only going to find the actual p-value, we're going to find the range from the table. We're going to kick it old school just a bit. So for this next one, a right-tailed hypothesis test, the sample size is n equal to 28, and the test statistic is 0.922. So I reckon we're going to have another high p-value here. So if we TCDF from 0.922 to a big number with 27 degrees of freedom, what would happen here is we would get a p-value of 0.1823. So if we went and checked out the table under 27 degrees of freedom, if you look, the critical values continue to get smaller and smaller. So, and 0.922 is off the charts, so that's why that's going to work. So yeah, that one is going to be off the charts again. Now, in a two-tailed hypothesis test, our sample size is n equal to 100, and our test statistic is negative 2.456. So what we're going to end up doing here is we're going to be multiplying this by 2. So we do 2 times TCDF from negative 100 to negative 2.456 with 99 degrees of freedom. So when we do that, what we get for this p-value here is going to be 0.0158. Now, so here's the thing. So if we look at sample size of 100, that's 99 degrees of freedom and 2.456. Now, 100, technically you should look at 99 degrees of freedom, so you could really look at 90 or 100. Now, if you remember, our t-value was 2.456. So let's see here, 2.456 falls right here. And if we look, the area in 2 tails has to be between 0.01 and 0.02. And it is. So you see how this all fits together, which is pretty darn neat. So a right-tailed hypothesis test, I have a sample size of 14, and I have a z-score. Oh, now I threw this back in just to make sure you were paying attention. Z, so we go back to normal CDF, 1.045 to a big number, and when we go ahead and do that, we get 0.148. So that's how all this works. I like to ask questions like this just randomly about p-values. You'll see some of these on your MyLabs. All right, now we're going to get into some where we actually have to enter the data. So what we're going to do here, these data, they've been changed slightly. And we're going to put TDA, we're going to put this list into L1, or list 1, and we're going to put this into L2. So, and before we do that, I do want to say we have to figure out the sample mean before we can make our conclusion whether it's a 1 or 2-tailed test. All right, so you enter the data into your calculator. Now, for this list here, so what I'm actually going to do here, I'm going to it's claimed that the average teacher salary in North Carolina is $45,600 per year. So what I'm going to do with that here is, first thing we should do is open up our calculator and let's do a 1-var stat on that first list. Now, if you've paid attention to the news and whatnot, you'll probably see that teachers' salaries are supposed to be lower. So someone will claim, oh, the teachers are getting paid enough. So here's the thing. So the null is that the mean is equal to $45,600. Alternatively, we think it's less than $45,600. So what that means is this becomes a left-tailed test. And since this becomes a left-tailed test, so we're going to figure out the t statistic based on this. So the t statistic is going to be 43,042. Let's call it 43,042. Let's just round to the nearest dollar. Minus 45,600. And our sample standard deviation is $4,406, and it's going to be divided by the square root of 32. So when we go ahead and do that on our calculator, so yeah, I'm going to do that on my calculator here. Whoops. We get a t-statistic of negative 3.284. Now, our alpha level was 0.01, and since this is one-sided, alpha was 0.01. So if alpha is 0.01 on one tail, this is going to correspond to a 98% confidence interval. So we're just going to do the 98%, by the way. So for the p-value, we would TCDF from negative 100 to negative 3.284 with 31 degrees of freedom. So when we do that, let's see what we get. And why is this thing doing this? All right, so yeah, punching this up into the calculator and going to paste it, we get a p-value of 0.0013. So based on that, what we would do is we would reject the null. Okay, come on. Yeah. Based on our p-value of 0.0013, we reject the null hypothesis. That means we have evidence favoring the alternative, and when we go with the alternative, we have reason to believe, in fact, I should say strong reason to believe, the true population mean teacher salary in North Carolina is actually below $45,600. So what we're now going to do is we're going to do a 98% confidence interval. Now remember why it's 98%, because this is a one-sided test. So if we go ahead and do that real quick, so we're going to do a 98% confidence interval now. So with 31 degrees of freedom and 98% confidence, let's see what our, 98% and 31, 2.453. So the margin of error is going to be 2.453 times 4406 over the square root of 32. And let's just round that to the nearest dollar. 2.453 times 4406 dividing by the square root of 32, and we are going to get $1,911. So our confidence interval will be 43,042 plus or minus 1,911. So what we get here out of this is 41,131 to 44,953. So our claimed mean of 45,600 is entirely above this, or we could say the entire interval is below that. So that's just further evidence that we would reject our null hypothesis. So if we base this on a sample of 32 randomly chosen North Carolina teachers, we are 98% confident that the interval from 41,131 to 44,953 captures the true population mean teacher salary for North Carolina teachers. So that's how that works. Now, if we go to the calculator again, if we go to stat and do a t-test, we have the data for L1, and we see the exact same thing here. And if we were to go do the t-interval based on our data, and remember, it's 98% confidence, yeah, we get exactly the same thing, which I think is pretty cool. So, for the second one here, we're only going to do the 98% confidence interval, and as opposed to doing this all by hand here, obviously we still think it's going to be less than, so equal to 45,600, and alternatively it is less than that. So what happens is when we go to do the t-test for this, and I will actually include any screenshots on here, we go and do a t-test, and we're going to change this now to L2. So having changed that to L2, if we go and calculate that, what happens is we're going to see that the p-value is indeed right on the money. Just like with the previous examples. So the purpose of pointing out here was that we could actually have, for tests for means, whether we have raw data or just statistics, we actually can, the hypothesis test and confidence intervals are very much directly connected. If we go to do the t-interval for 98% confidence, we see that 45,600 is, as a matter of fact, right on the money. And again, I would not give you one like this on a test where it's right on the money. But as you can tell here, the p-value, it's not exactly 0.01, but it's close enough, and it's right on the cusp here. Alright, so I'm going to conclude this video right here. Now, the last part of this will deal with hypothesis tests and confidence intervals for proportions. That'll be kind of a different animal here. So I hope you enjoyed this, and have a great day. Alright, so welcome to what I believe should be the last video in this unit. We're going to talk about everything with proportions now. So that's what the focus of this video is going to be. So what we're going to do in this video is we're going to see how proportions work, and we're going to see the disconnection between hypothesis test and confidence intervals. So that's how proportions are going to work for this. So in the following setting, we need to determine the point estimator we would use to calculate the value of the point estimate. So what proportion P? Notice that this P that we speak of does not have a hat on it. This P is the population proportion. So what we have to do as an estimator is we have to come up with P hat, which is in fact the point estimate. So it is the number of successes in a sample divided by the number in the sample. So in 2007, the Youth Risk Behavioral Survey questioned a random sample of 14,041, and 2,808 of them said that they have smoked
cigarettes at least one day in the past month. Oh, naughty, naughty. You know, getting a little personal, I've never smoked a thing in my life, and I don't ever plan on starting. So, if we want to figure this out, we take 2808 divided by 14,041, and let's just call it zero point 0.2 or 20%. So, yeah, and those of you that are older students, some of you that are older than me, might actually remember when schools actually had smoking areas for students and teachers. So, yeah, schools definitely don't do that anymore. So that's our point estimate p hat. Now, the margin of error E is called the maximum error of the estimate and can be found by multiplying the critical value. Guess what? We're back to critical values again, and the standard deviation. Now, the standard deviation of the sample proportion is represented by this, square root of p hat q hat over n. So, guess what? Now we're going to talk about confidence intervals real quick. So, it has to be a simple random sample. Yeah, that goes without saying. And there'd have to be 5 successes and 5 failures. Some textbooks would actually use 10 and 10. So those are the conditions or requirements. So first thing you got to do is verify, round it to 3 significant digits, by the way. So what you need to do here is you need to verify that the conditions are in fact satisfied. Data come from a simple random sample. Conditions for a binomial probability are met. And if they are, you're good. So we determine the critical value of z sub c, determine the margin of error, and calculate the endpoints, and then interpret. So, in a survey of 1,000 United States adults, 662 said it is acceptable to check personal email while at work. We're going to construct and interpret a 99% confidence interval. Now, we're also going to use the calculator to sort of verify things. So first thing we need here is the sample proportion, and this is actually really easy. 662 out of 1,000, which is 0.662. Now, Q hat is 1 minus 0.662, or I believe that is 0.338. Yep, 0.338. So, now 99% confidence. Now, notice that we're using Z again. We're back to the Z. So if you go to printout, if I go back here to the table, I want 99% confidence, and why this is taking forever to load, I don't understand why. So 99% confidence, our critical Z value is 2.576. So our margin of error, and we'll round this to 3 decimal places. So we take 2.576 times 0.662 times 0.338 over 1,000. So that's going to give us our margin of error, and if I go to calculate that, make sure I'm back on the calculator, 2.576 times the square root, and I'll set up a fraction on the inside, 0.662 times 0.338, and then we divide by 1,000, and we get 0.038 or 0.039. So that's going to be our margin of error, 0.039. So the confidence interval is going to be p hat plus or minus our margin of error. So in doing that, what happens is we get 0.662 plus or minus 0.039. So we figure out the endpoints, 0.662 minus 0.039, 0.662 plus 0.039. So we get 0.623, and instead of a mu for mean, we're now going to have a p between, and we'll have 0.701. So we can now interpret this based on a sample of 1,000 US adults. We are 99% confident that the interval from 62.3% to 70.1% captures the true population proportion of U.S. adults who believe it is acceptable to check personal email while at work. So that's our interpretation. Now, let me expand this calculator just a bit. So if we go to stat and under tests, we're going to choose, we're going to do one prop z interval. X is the number of successes, 662 out of 1,000, and our confidence level is 0.99. And we get exactly this. So, pretty neat how this works. I thought so. All right, so I hope you're getting this because it's good. All right, so now a Pew Research Center poll of 800 randomly selected adults showed that 613 respondents know what Twitter is. So the point estimate for p hat is going to be 613 out of 800. And so if we go ahead and figure that out, we get 0.766. So to find the margin of error, now this decimal does terminate. You can take it to more decimal places if you want, but 3 is really enough. So if we find the margin of error E that corresponds to a 95% confidence level, so we can verify, we can do this with the calculator. 95%, we have 1.96. So we get 1.96 times 0.766 times 1 minus 0.766, and that's going to be divided by 800. And when we go to figure that out, what do we get? We get 0.029. So the 95% confidence interval is simply going to be 0.766 plus or minus 0.029. So, point, oh, I have to switch over to this. 0.766 minus 0.029. And we get 0.737. I keep forgetting I got to do this. So we get 0.737 to 0.795. So the interpretation is based on a sample of 800 adults. We are 95% confident that the interval from 0.737 or 73.7% to 0.795 or 79.5% captures the true population proportion of U.S. adults who know what Twitter is. So this is actually a very old problem here. This was before, I mean, yeah, it's still pretty confident. All right, so this last part here, I actually forgot to kind of submark these problems. So more than 75, more than, and then C. So more than 75. So do more than 75% know what Twitter is? Well, if you remember, the interval goes from 0.737 to 0.795. 75% is inside of this. And since that's the case, we cannot safely conclude. Unfortunately. Now, what about 80%? Well, 80%, more than 80%, definitely no. But less than 85. Here's the thing. 85%, yes. And the reason is because the entire confidence interval is below the 85% mark. Now, we're going to be doing some of these to see how they're connected with hypothesis tests and whatnot in a little bit. All right, so let's do the calculator with that just for good measure here. So we want the one prop z interval, and this time we have 613 out of 800. And this time we want 95% confidence. And what we see here to 3 decimal places, it's a little off from our calculations by hand, but that's okay because it, we rounded to 3 decimal places. That should be fine. So that's how it'll work. All right, so some things to know when you're analyzing polls. Now, right now it is April of 2020. One thing you'll see is, so the sample has to be a simple random sample, not a voluntary response sample. The confidence level should be provided, but media often neglect to simply identify it. They should provide the sample size, and the quality of the poll depends on the sampling method. Now, of course, I lost my faith in pre-election polling back in 2016 for obvious reasons. So, the only really reliable poll is what happens on election day. That's just my opinion. So let's say we want to collect sample data to estimate a population proportion. Now, let's say, how many must we have? So if we calculate our margin of error formula and solve it for n, we get this. Now, you can replace the P and Q with both 0.5, and that'll give you the most conservative estimate. So, let's say for a 95% confidence interval, 95%. So, what happens here, 95, that is 1.96. So, what happens here is we want to find the proportion of students that have been arrested. How many must we sample for a margin of error of 4%? So E is 0.04. So if we know a previous proportion to be 30%, that means we could either let P hat or Q hat be 0.30, and it follows that Q hat is going to be 0.70. So N is going to be 0.3 times 0.7 times 1.96 divided by 0.04 and squaring that. Now, we go to figure that out, 0.3, 0.7, 1.96 over 0.04, and then squaring, we get 504.21. However, even though it technically rounds down, you must round up in any event of sample size calculation. So we get 505. Now, what if we didn't know anything about a previous proportion? So we would let p hat be 0.5 and q hat be 0.5. So in that case, n would be 0.5 times 0.5. The critical z of 1.96 is still there, then 0.04. So all we have to do here is just replace the 0.3 and 0.7s with 5s. And we get 600.25. But it has to be rounded up to 601. So, did you know that we can find a point estimate margin of error based on a confidence interval? So, let's say we have a confidence interval of 0.324 to 0.406. So, just like with means, confidence intervals over about proportions are strictly symmetric. So, if we take 0.406 minus 0.324, we get 0.082. And if I divide that by 2, our margin of error is going to be 0.041. Now, there are so many different routes that you could take to this. If we do 0.324, take 0.324 and 0.406, and then divide that by 2, we get a point estimate p hat of 0.365. Now, so you could have found the point estimate first or the margin of error. You could have done 0.365 minus 0.324 and gotten it that way, a 0.041. So many different ways to do this that, you can do it. So that's what you'd get. All right, so let's say we're running a political campaign and wish to estimate with 99% confidence, rather, the proportion of registered voters who will vote for your candidate. So, for 99% confidence, what that means is our critical z value, 99% confidence, that is going to be 2.576. And our margin of error is 0.03. So if we want to find a required sample size, if no estimate is available, that means we would use 0.5 for p hat and q hat, and then multiply that by 2.576 over 0.03 and squaring that, and let's see what we get. Times 2.576 divided by 0.03, and we square that, we get 1,843. Well, actually, we get 1,844. That's a lot. Well, that's typically how many get pulled. We need more to pull, basically. So if we have a preliminary estimate of 32%, that means we would take 0.32, and one less than that is 0.68. And then the 2.576 over 0.03 again, and don't forget to square it this time. So what we got to do here is 0.32, and then 0.68, 2.576 576 divided by 0.03, and we square that. In this case, we get 1605. So, yeah, it goes to show that if we know nothing about it, that gives us our highest possible estimate. So, that's how this will work. So now we're going to talk about a hypothesis test here. So if you go to page 38, let's say a basketball player claims to be an 80% free throw shooter. And what happens is, to test this claim, we're going to have him attempt 50 free throws. And he makes 32 of them. And what happens is, the sample proportion of made shots is 32 out of 50 for 64%. So what can we conclude? So what we're going to do here is we're going to use software to simulate 400 sets of 50 shots, assuming that the player is really an 80% shooter. So in other words, we're assuming that claim is going to be true right off the bat. So we can say how strong the evidence against the player's claim is by giving the probability he would make as few as 32 out of 50 if he really makes 80% in the long run. And the observed statistic is just so unlikely that the actual parameter value, it gives convincing evidence the player's claim is not true. Now, what happens here is there are two possible explanations. Player's claim is correct, and by bad luck, a very unlikely outcome occurred, or the population proportion is actually less than 0.8, so it's not an unlikely outcome. I always like to bring this up. In the world of professional hockey, one of the best goaltenders of all time, probably one of the greatest in North American history, is Patrick Waugh, who played for the Montreal Canadiens and Colorado Avalanche. And as a matter of fact, I'm going to show you, I'm actually going to show you something kind of cool here. So what you see on my screen is Patrick Waugh basically, he gives up several goals. He gives up 7 goals in the first period of the game. Now, any coach with half a brain would have pulled their goalie and said, you know what, it's not your night, sit down, relax, but this coach had a vendetta against him, and the problem was, that ended up resulting, this coach kept Patrick Waugh to humiliate him, kept him in the net just to humiliate him, and it basically ended his career in Montreal. So, it was just a bad night. Another one I like to point out is in Super Bowl 30, that was back in 1997, or 96, I should say. Neil O'Donnell, the quarterback, was actually investigated to see if he threw the game because he was one of the most accurate quarterbacks in history at the time, and he threw 3 interceptions, 2 of which were returned for touchdowns. So, again, it's very possible you have a bad day. So the rare event rule for inferential statistics basically states that if under a given assumption, the probability of a particular event is exceptionally small, we conclude the assumption is probably not correct. Well, that goes to show that's pretty basic to say here. So what you could do here, let's try an example here. So let's assume 100 babies are born to 100 couples treated with the X-sort method of gender selection. So what we're going to do here is we're going to see if that XSort method of gender selection makes girls more likely. Now, I don't know why you'd want to do that. You shouldn't be able to dictate what you have. You have a baby, but so test statistic, statistic minus the parameter, and it's divided by the standard deviation of that statistic. So, this computer. So these shouldn't have p's here now, and what happens is the statistic was 0.58. The parameter or the claim value was 0.5. And standard deviation, we're using the claimed p. We're going to use the claimed p instead. So it's a one-sided test. So if our alpha level is 0.05, one-sided, and our critical value is 1.645. So what happens here is if it were 1.645, this red region is in fact our rejection region. So if you remember that from way back, now what happens is our actual value of 1.6, it was close. So we are going to fail to reject. So yeah, we will fail to reject the null. Now let's figure out the p-value. So the p-value, we want 1.6. So we get back into normal CDF. So 1.6 to some big value, and we get a p-value of 0.0548. So we fail to reject the null. And what that means in the context of the problem is simply that we fail to reject the null and have evidence that the XSort does not necessarily work, which is fine. So yeah, if you're still confused about hypothesis testing, don't worry. So again, we're harkening back a bit to our hypothesis testing. Why do we fail to reject the null as opposed to accepting the null? So what happens here is, we fail to reject the null, and the purpose of that is, we don't accept it. So if you remember, in context, a type 1 error, we rejected the null incorrectly. We went with the alternative. We believed, in fact, I'm going to change this a bit here. We believed XSort worked, but it really did not. In fact, I'm going to try to change this a bit. Yeah, there we go. So what is a type 2 error in the context? Well, in this case, we failed to reject the null incorrectly. So we believed XSort did not work, but in all reality, it really did. It really did work. So that's how that'll work. trouble here. Let me get this fixed. There we go. So a z-test for a population proportion, the standardized z-statistic is that. So what we're going to do here is we're going to do a hypothesis test here, and we're going to see how this connects to a confidence interval. Now, so we're also going to do some confidence intervals just to see how they connect here. So it's claimed the nationwide cheating rate is 71.25%. Now you're probably wondering, where did that come from? Well, it came from various places here. So basically, the null is that the proportion is 0.7125. Alternatively, the proportion is really greater than 0.7125. So what we're going to do with that is we're going to see just how this connects. So we need to figure out the z-score, and 748 out of 1,000. So basically, p hat is 748 out of 1,000 for 0.748. So we get 0.748 over 0.748, this computer, minus 0.7125. And we divide that by 0.7125, 1 minus 0.7125, and that's going to be divided by 1,000. So we need to figure out what the z-score for this is in fact going to be. So using the calculator, 0.748 minus 0.7125, and then we set up a fraction underneath this. 0.7125 times 1 minus 0.7125, then dividing it by 1,000. And we get a z-score of 2.48. And what we want is we want the area that is to the right of this. So 2.48. So the p-value, we would normal CBF from 2.48 on. And get 0.0066. So in this case, we reject the null, and we have evidence to suggest the nationwide cheating rate may be higher. So one thing we can do here is if we go to the calculator and go to stat and then tests, do a one prop z test, 0.7125 and 748 out of 1,000, and we think it's later above that, and we get the statistics just like this. Now, what'll happen here is when we go ahead and do this, what you should see, this is a one-sided test. So if it's a one-sided test of 0.05, that's going to correspond to a 90% confidence interval. Now, I'm actually going to cheat a little bit here and do the confidence interval calculation right here. So 748 out of 1,000 with 90% confidence. If I do that, in fact, I'm going to paste this right to here and copy it down. So what happens here is, based on a sample of 1,000 students, we are 90% confident that the interval from, I have to fix this again, from 0.725 to 0.771 captures the true population proportion of college students who've cheated in some way. Now, so that's going to be that one. Now, if we go to the next one here, we're going to have a slightly different outcome here. Now, our point estimate now, 736 out of 1,000, or 0.736. So what we're going to do here is I'm just going to carry out the test on the calculator. So if I go and do a one prop z-test, this time, 736 out of 1,000. And what we see is the p-value is going to be right on the money. Now, if I go and do the interval, one prop z interval, we're going to get that. So what happens here is there's going to be something slightly different here. Now, based on this, we'd fail to reject the null. This is really on the cusp. So what happens now, for the interval, the entire confidence interval is above 0.7125. So what happens is we would actually get a different outcome. So confidence intervals and hypothesis tests for proportions can have different outcomes if the test statistic is close to the edge or cusp. So we would actually make a different decision here. So this is where things are just a little different, but that's okay. All right, so we've got a couple of problems here to work on. Yeah. So a research center claims that less than 50% of U.S. adults have access to internet over a wireless network. So in a random sample of 100 adults, 39%, so p hat is 0.39. If n is 100, now here's the thing, x would be 39 successes if you were doing this in the calculator. So that's just a little FYI, so to speak. So the null is that p is equal to 0.5. Alternatively, it's going to be less than 0.5. So the z-score is going to be 0.39 minus 0.5, and then we divide that by 0.5 times 0.5 over 100. And so we figure out that statistic, and what we get here is negative 2.2. So this is a left-tailed test. So here's negative 2.2. The p-value, we would just have to normal CDF, and we get 0.0139. So in this case, at an alpha level of 0.01, we fail to reject the null. Now, in addition, what I'm going to want here is I need this in context of what happens. So in the context of this problem, what happens is we fail to reject the null. We have reason to believe that the research center claim of less than 50% of adults use wireless may be incorrect. And again, we can't say, oh, it is or isn't. We have evidence to suggest. That's how hypothesis testing works in statistics. So with that in mind, so a research center claims for this next example, 25% of college graduates think a degree is not worth the cost. So what happens here, I'm actually just going to do this on the calculator real quick. So 1 proportion z-test, the claim is 0.25 and 21% of 200, so that would be 42 out of 200. And if we go less than that, we would actually reject the null at this. I'm actually going to skip on down to this last one here. So, based on information from the National Cybersecurity Alliance, 90% of computer owners believe that they have antivirus. So, what happens here is, the null is that the proportion is 90%. Alternatively, and I would actually have rewritten that to say we think it's greater. But 372 out of 400 have antivirus, which is 0.93 or 93%. So the z statistic is 0.93 minus 0.9, and we divide that by 0.9 times 0.1 over 400. And let's see what we get here. We get a z statistic of 2. So if we normal CDF that from 2 on, so I didn't give you an alpha value. We're going to say, alpha is 0.05. So based on our p-value of 0.0227, we reject the null and have reason to believe that the true population proportion of computer owners with antivirus is over 90%. Now, if we go to this one here, was an interesting one here. We let alpha be 0.05. Now, let's say, let's change this now. Instead of 400, we're going to have 100. So 0.93 minus 0.9, now 0.9 times 0.1, but over 100. So The Z statistic for that is going to be 1. So what happens is, if we normal CDF that, this time from 1 on, we get 0.1587. So in this case, we fail to reject the null, as our p-value of 0.1587 is higher than the alpha value. So you're probably thinking, wait a second, it's the same sample proportion, but what happened here was exactly, basically a larger sample can enable a test to be more easily rejected as opposed to a smaller sample. Larger sample also yields more power. All right, so yeah, so that is it for this video, and I hope you've enjoyed. So thank you very much for listening, and have a good day.